Welcome to the module on sustainability aspects of battery recycling and second life. This module focuses on how we scale batteries responsibly by reducing environmental impacts, managing safety risks, and strengthening resource security. Sustainability matters because batteries are expanding rapidly and will shape energy, transport, and digital systems. Without it, growth can intensify pressure on critical raw materials, worsen mining and refining impacts, and increase end-of-life waste. A sustainable battery value chain cuts greenhouse gas emissions, protects water and ecosystems, and limits toxic releases through responsible sourcing, efficient manufacturing, and controlled end-of-life management. It also improves resource security by increasing material efficiency and scaling high-quality recycling. Extending battery lifetimes and enabling second-life applications where appropriate further reduces impacts by delivering more service from the same materials. These measures lower reliance on virgin extraction and strengthen supply resilience. Sustainability also supports economic resilience and public trust. Clear standards for safety, transparency, and environmental performance reduce regulatory and liability risks, attract investment, and stabilize markets for recycled materials, making responsible scaling practical, not optional. The environmental footprint of battery materials is driven mainly by upstream stages: mining, refining, and precursor manufacturing. These steps are often energy-intensive and can account for a large share of life cycle greenhouse gas emissions, especially when powered by fossil-based grids. Extraction and processing also create non-climate impacts, including land disturbance, ecosystem damage, and waste generation. If environmental controls are weak, local air and water pollution can be significant. Water use and water quality risks are critical in several supply chains. Material production can require substantial water and can generate contaminated effluents, while global transport across multiple countries adds further emissions and environmental burdens. Footprints vary by chemistry and material mix. Cobalt and nickel-based cathodes often have higher upstream burdens, but all chemistries rely on inputs like aluminum, copper, and graphite. Reducing impacts requires cleaner energy, higher material efficiency, longer lifetimes, and strong recycling that displaces virgin production with secondary supply. Battery recycling provides clear environmental benefits by diverting hazardous materials from landfills and reducing demand for virgin mining and refining. Recovering lithium, cobalt, nickel, manganese, and lead conserves finite resources and often lowers energy use and greenhouse gas emissions versus primary production. It also reduces local pollution and health risks when handled through proper collection and controlled treatment. This prevents toxic releases, such as lead and acidic electrolytes from lead-acid batteries and reactive electrolytes or metal-bearing residues from lithium-ion systems, into soil and groundwater. Well-run recycling facilities mitigate safety risks, including fires from improper storage or disposal, and manage wastewater, dust, and solid residues using emissions controls and waste treatment. These safeguards are essential to avoid shifting impacts from one pathway to another. Recycling supports a circular economy by turning end-of-life batteries into inputs for new products. Higher recovery yields, improved purification, better collection, and design for recycling with traceability maximize displacement of virgin materials and strengthen a more resource-efficient energy system. Battery recycling can deliver strong sustainability benefits by recovering valuable materials and reducing reliance on virgin mining, but it also introduces environmental trade-offs. Outcomes depend on the chosen process, energy sources, emissions controls, and how wastewater and solid residues are treated, since impacts can shift between climate, air, water, and hazardous waste. A key trade-off is energy use versus recovery efficiency. Thermal processes handle mixed feedstocks and simplify separations, but high temperatures increase energy demand and require robust off-gas controls for particulates and hazardous emissions. Hydrometallurgical routes can achieve high recovery and battery-grade purity, yet they depend on chemical reagents and can generate wastewater, salts, and sludges that require neutralization and secure disposal. Mechanical pre-treatment can reduce downstream processing needs, but it may create fine dust and material losses if containment and filtration are insufficient, making controls and operational discipline essential. Battery recycling involves important safety and logistics trade-offs, particularly for lithium-ion batteries. Transport, storage, and dismantling can create fire risks, requiring controlled discharge, certified packaging, and trained handling. These safeguards reduce incidents but add cost and can increase operational energy and material use. Producing higher purity, Battery-grade, recycled materials can also require extra processing steps. While this improves circularity and market value, it may raise energy demand and generate additional secondary wastes. Because impacts vary by process and site, recycling performance should be assessed using detailed mass balances and life cycle assessment with measured data on emissions, effluents, residues, and energy use. This avoids overstating benefits or overlooking shifted impacts. The most sustainable outcomes typically combine high collection rates, efficient pre-treatment, low loss separations, clean energy inputs, and rigorous pollution controls. This ensures material recovery benefits are not offset by new impacts in air, water, or hazardous waste streams. Second life batteries can improve sustainability by extending use before recycling, increasing the total energy delivered per unit of material and manufacturing impact. Batteries that no longer meet first-use requirements may still be suitable for less demanding applications such as stationary storage, backup power, or renewable buffering, which can defer new battery production and reduce near-term demand for materials. The net benefit depends on the added processes required for reuse. Testing, diagnostics, disassembly, repackaging, and integration add energy and materials. Benefits are strongest when these steps are efficient and standardized, and smaller when they are complex, manual, or require major component replacement. Safety and reliability are essential. Second life systems must meet standards for electrical protection, thermal management, fire prevention, and transport, supported by clear liability and robust quality grading to ensure predictable performance and avoid incidents. Second life should be treated as a step that delays, not replaces, recycling. At the end of second use, batteries should enter controlled recycling streams to recover materials and prevent leakage into waste or informal disposal, supporting a more resource-efficient energy system. Improved battery end-of-life management delivers major sustainability gains through waste reduction and resource conservation. Batteries contain valuable, and sometimes hazardous, materials, so landfilling or improper handling wastes resources and increases risks of contamination to soil and water. Controlled collection systems reduce hazardous waste and prevent pollutant release. Recycling and reuse conserve resources by returning materials to supply chains and reducing the need for virgin extraction. Recovering lithium, cobalt, nickel, manganese, and lead, along with copper, aluminum, and graphite, lowers mining and refining demand and associated land disturbance, energy use, and emissions. Second life applications further improve resource efficiency by extending service before recycling and delaying waste generation. Maximizing benefits depends on high collection rates, efficient sorting and pre-treatment, and recycling that achieves high recovery yields and product purity. Designed for recycling, standardized labeling, and strong traceability reduce losses and improve output quality. When these conditions are in place, battery circularity becomes a practical pathway to reduce waste, conserve critical resources, and strengthen supply security. Safety, health, and environmental risks must be managed across the full battery life cycle, especially during collection, transport, storage, disassembly, and recycling. Spent batteries can retain charge and contain reactive or corrosive electrolytes, creating risks of short circuits, thermal events, chemical exposure, and environmental releases, particularly when damaged or mishandled. Risks vary by chemistry. Lithium-ion batteries present fire and thermal runaway hazards during mechanical stress, and leaks can create harmful emissions and contaminated residues. Lead-acid batteries pose severe risks due to lead toxicity and sulfuric acid, with potential for dust, fume releases, soil and water contamination, and high occupational exposure. Nickel-based systems involve heavy metal risks, and nickel-cadmium is especially critical because cadmium is highly toxic and must be strictly contained. Effective risk management depends on strong procedures and engineered controls. Core measures include safe discharge, certified packaging and transport, ventilation and dust capture, fire detection and suppression, closed-loop electrolyte handling, and rigorous wastewater and residue treatment. Worker protection and oversight are essential. Training, exposure monitoring, personal protective equipment, and hygiene practices reduce inhalation, ingestion risks, while regulatory enforcement and traceability help ensure compliant processing that protects workers, communities, and ecosystems. Design for sustainability integrates environmental, safety, and circular economy requirements into battery development from the outset. Because material choices, cell architecture, and pack construction lock in much of the footprint, design decisions strongly shape manufacturing impacts, service life, and the practicality and cost of reuse and recycling. Design for circularity enables longer use and easier recovery. Standardized pack formats, modular architectures, and accessible fasteners simplify disassembly and support repair, remanufacturing, and second life applications. Clear labeling and traceability improve sorting and routing, while battery management system accessible state of health data reduces diagnostic cost and strengthens safety screening. Sustainable design also involves smarter material and process selection, reducing reliance on scarce or high-impact inputs, improving material efficiency, and enabling high recovery yields can lower upstream burdens and strengthen supply security. Safety features are equally critical, including measures that limit thermal runaway propagation, improve abuse tolerance, and reduce electrolyte leakage. When paired with standards, regulations, and producer responsibility, sustainability-oriented design makes recycling more efficient, second life more viable, and the overall battery value chain safer and more resource efficient. Policy and governance are essential to make battery recycling sustainable, safe, and economically viable at scale. Because batteries contain valuable and potentially hazardous materials, voluntary collection and market forces often do not deliver high return rates, consistent feedstock quality, or strong environmental performance, so clear responsibilities across the value chain are needed to keep end-of-life batteries in regulated channels. Extended producer responsibility is a core mechanism, requiring producers to finance and organize collection and end-of-life management. Paired with collection targets, take-back obligations, and transparent reporting, extended producer responsibility improves return rates and stabilizes recycler feedstock supply. Standards and technical rules reduce risk and raise performance. Requirements for packaging, transport, storage, discharge, and dismantling lower incident rates, while recycling efficiency and material recovery targets drive better resource outcomes. Design, labeling, and traceability tools improve sorting, safer disassembly, and higher quality recycled outputs. Governance must also protect communities and ensure market integrity. Strong permitting, monitoring, and enforcement control emissions, wastewater, and residues and help prevent illegal exports. Policies that build secondary material demand, quality specifications, public procurement preferences, and incentives for closed-loop manufacturing reduce investment risk and support a competitive circular battery economy. To conclude, sustainability matters because batteries are scaling fast and can amplify pressure on critical minerals, emissions, and waste if unmanaged. It provides the framework to keep growth responsible while preserving the benefits batteries deliver. Most environmental burden sits upstream in mining, refining, and precursor production, often powered by fossil energy. Land disturbance, air impacts, and water use, effluents can be significant, and long supply chains add additional emissions. Circular strategies cut waste and conserve resources by keeping batteries in controlled collection systems, enabling second life use and recycling metals back into supply chains. High collection rates, good sorting, and high yield, high purity recovery are what make the gains real. Finally, safety and governance are the enablers. Batteries carry fire, chemical, and heavy metal risks across transport, storage, disassembly, and recycling. Strong standards, engineered controls, EPR, and traceability keep flows regulated, protect people and ecosystems, and support stable markets for recycled materials. Thank you for your attention.